Okay, so exercise 7 here wants us to write a function to convert the Luther image from regular full color into grayscale. Now, to be able to do that, we have to figure out what is grayscale. So, uh, you know, like we tell you all the time in this class, you've really got to get adept at Googling for that sort of information. So I did Google for it. I typed in RGB to grayscale conversion, and this was one of the first articles that popped up, this tutorial point article. So it says that if we already have an RGB color module, RGB colors available for the picture that we're looking at, to move it from this to grayscale is actually relatively simple. What you need to understand is that for a color to become gray, or any shade of gray, is expressed in RGB as matching values. So that goes all the way from black, which is 0, 0, 0, 0 red, 0 green, and 0 blue, all the way up to pure white, which is 255, 255, 255. So grays are going to be anywhere in between there. It could be 13, 13, 13. It could be 85, 85, 85. But if all three of your colors, red, green, and blue, have the same values, you're going to get a gray pixel. So in order to write a conversion that does that, what we have is this. Grayscale for any pixel is going to be equal to the values of its red, green, and blue pixel divided by 3. So like this says, we're averaging it. We're averaging it using the average method. You just take the average of the values of your 3 colors. So you add up the value of red, the value of green, the value of blue, and you divide it by 3 and set each of those to be that value. So your red, your green, and your blue are all going to become equal to R plus G plus B divided by 3. So what you need to do is back in here. I just copied over the same stuff I was doing before because we're doing the exact same thing. Except this time, instead of getting rid of the red value, we're going to make sure that we get the red value. And then we need to create a gray value. Now, if you look back over here, our gray value we know is going to be equal to R plus G plus B divided by 3. And we already found those values. We have them right up here. So we can just do that. Gray is equal to red plus green plus blue divided by 3. And so it's going to store whatever the current pixel's value in grayscale would be to this variable gray. And then we're just, instead of creating a new pixel where we have red, green, and blue equal to, the red, green, and blue values of the new pixel equal to the red, green, and blue values of the old pixel. Instead, we're going to set them all equal to the same value, to gray. Because a grayscale pixel, a gray pixel, is going to be a pixel where all the 3 colors have the same value. So, for example, if our red, our green, and our blue add up to equal 90, then 90 divided by 3 equals 30. So each of our RGB values is going to be equal to 30 in our new pixel. So that's all I need to do. That's all I need to change for this. So I'm going to save my code, and I'm going to run it. I'm going to let it load up here for a second. And there we go. That's it, a grayscale picture. And that's using the average method. Now, generally speaking, the average method isn't the best way to do grayscale. If you kept reading this article, you would see like there are more complex combinations of RGB values that people use to get a weighted grayscale image, or a grayscale image that tries to preserve luminosity rather than an average image, which tends to come out looking a little bit darker than the actual picture. So if you wanted to do a grayscale image using the weighted method or the luminosity preserving method, you would want to use this right here, this value, rather than the value of all of them added together and divided by 3. And we can do that really easily. So if I take this, I see that I need to multiply red by 0.3, green by 0.59, and blue by 0.11. So I'll do that. And I'll just do that right here. So instead of red being equal to get red, we're going to equal it to red, to pix.getRed times 0.3. And green is going to be times I believe it was 5.9. We can switch back over here to check. Yep. And blue is going to be equal to get blue times 0.11. Oops. And then we can just get rid of this divided by 3. So now I have a version of this grayscale image making program that's going to make a grayscale image that, instead of average grayscale, which tends to be darker, it's going to be luminosity preserving grayscale. So let's give that a click. We'll run it and see if that changes our image at all. There we go. Yeah, slightly imperceptibly, but a little bit different. I can see that it preserves this shadow a little bit better down here, and that might not come across in the actual video, but it preserves the shadow down here a little bit better rather than washing it out to a more pure black. I can see the actual bell ringer down here a little bit better, and the definition on a lot of these bricks and stuff and the shadows along the brick edges here is a lot better. So again, not necessary for this exercise, but kind of a cool way to show you that, like, you can find that information out there and apply that using what you already know. So again, the rest of these problems all work kind of the same way. So we'll try to go through them and really knock out the rest of this.